The next three talks and the final three talks will focus on a slightly different theme than we've really seen so far, but there's still a strong intersection with what we've done. And the big addition here is now bringing in crystal plasticity. And one of the key effects of that is that your material becomes anisotropic, and that's something that you can measure. And so by measuring that, you get some indication of how the crystal plasticity is playing a role during the deformation. And so what's going to happen is Neil will start giving us a sense for what the state of the art is in dealing with crystal plasticity and crystallographic alignment in dry, melt-free olivine polycrystals. And then I'll talk at you for a little bit, looking at some of the laboratory results that go along with this, but also then adding into the effects of a melt phase, and things start to get weird then. And then finally, after the coffee break, Andrea Tomasi will give a presentation, then bringing in a lot of observations from rocks in the field. And as you might expect, going to a real system, things get even more complicated. So we'll start with the dry melt-free case from Neil.
Okay, well, thank you very much for the introduction and to the organizing committee for inviting me. As Lars said, this is the first of three talks on roughly related themes. I'm going to talk about the evolution of anisotropy in olivine polycrystals, which are dry.
Turn your mic on, I think.
I should mention that much of this work was done by postdoctoral fellow Neil Golding. Oops.
Is your mic on?
Oh, thank you. Is that better? No. It's on now? Okay. I can't tell. It's a red light. Okay. So why do we care about seismic anisotropy? First of all, a definition. It's the dependence of elastic wave speed on the direction of propagation in the material. Its cause is non-random crystal preferred orientation, often called CPO, of anisotropic minerals. And the case I'm going to be talking about is olivine, so that would correspond to depths in the mantle of 410 kilometers or less. What about the origin of LPO, of CPO? It's the progressive direct deformation of mantle rocks via dislocation creep, that's important, which causes crystals with different orientations to rotate at different rates. So the utility of it is that anisotropy is a direct consequence of deformation, and therefore can be used to constrain the pattern of mantle flow. It used to be said that seismic anisotropy would allow us to map convection in the mantle, but that's I'd say is quite exaggerated. Saying constraints is more limited, more true. But to do this, we need, as a preliminary, a theory for the relation between the velocity gradient tensor in the flow and the rate of change of CPO. I'll explain what I mean by that in a while. Obviously, we need to establish the link between deformation and the preferred orientation that forms in the rock. Just a couple of maps to show you the distribution of seismic anisotropy over the Earth's surface. This is from Long and Becker, 2010, and the white bars are the magnitude of azimuthal anisotropy, the anisotropy that depends on the azimuth of the surface wave. You can see also some gray bars here that are very hard to read. So this is somewhat simpler. From the same paper, they're looking at the distribution of anisotropy in subduction zones around the Earth. And you see the red arrows, these things here, are the subslab anisotropy, so here in a little cartoon version of a subduction zone. And the blue represent the mantle wedge anisotropy. And with some exceptions, the anisotropy subslab is parallel to the subduction zone. It's also true for the mantle wedge anisotropy, but there are exceptions. So the question is, what does this tell us about the flow in the mantle? Well, here's a bit of motivation for the problem. Self-consistent methods based on homogenization are widely used to model preferred crystal orientation in mantle rocks, but they're very heavy, they're too slow to use in the context of a convective simulation, for example. So what I'm going to try to do today is show a proposal for an efficient new algorithm, which I call ANPAR, for analytical parameterization, which is, on the one hand, orders of magnitude faster than current methods, and which agrees exactly with the predictions of the state-of-the-art homogenization model, the so-called second-order self-consistent model. I say exactly, that may sound arrogant, but I really mean it, and you'll see why. So I should say the self-consistent model was proposed with Ponte Castañeda in 2002, so it's a fairly recent model. So I wanted just to show you the mechanism of crystallographic rotation in a very simple experiment with books on a shelf. So imagine I have my books with that are inclined to the shelf, and I want to deform that stack of books in pure shear. Well, obviously books can't deform in pure shear, they have to do something else. They can only deform by sliding along the interfaces between them. So I push down the books and I get, oops, I'm getting ahead of myself here. You get a spin, theta dot here. The angle of the books has changed. And you can now, this is a definition of what's called a slip system. Slip system consists of two vectors. One is the direction of slip, so that would be the vector L here. And the normal to the slip plane is the vector N. You'll see those later on. So the generalization to 3 dimensions is the following. Now instead of a single angle theta here, I have 3 Eulerian angles, phi, theta, and psi, which are often called boldface G, just for short. And you can see the definitions of the Eulerian angles are over here. And we also have a spin, 3 components of the spin of the crystals. That's essentially the 3-dimensional version of this spin of the books. So again, those spins are lumped together in a single symbol, which is called G dot. Okay, well, let's now think about the slip system rheology. I've told you what a slip system is, this combination of 2 vectors. We assume that the slip system rheology is a power law with a shear thinning rheology. So the shear rate in that case is proportional to the resolved shear stress on the slip system, that's tau, to the nth power, and the normalization factor is this critical resolved shear stress, it's often called, which I'll denote by tau superscript s. And finally, n is the power law exponent, which experiments show is around 3.5. So the slip systems I assume in this work are the following. There are 3 dominant slip systems in olivine, 1, 2, and 3 here. The slip plane of each slip system is listed here. The slip direction here. The ranges of values of the ratios of the critical resolved shear stresses that I'm using are the following. So slip system 2 will always be the reference, and slip systems 1 and 3 I vary over a large range to get scaling laws. The exponent, as I said, is 3.5. You'll wonder, what about these things down here with the very strong slip systems, 100 typically. This is a trick to get convergence. If you put only the first 3 slip systems in your model, the numerical code doesn't converge. You need at least 4. And so these are slip systems which are very hard. They have a large critical resolve shear stress. So they don't slip very much. They're resisted against slippage, but they affect strongly the rheology of the predicted rheology of the aggregate. So what I'm talking about here is a method that can predict the preferred orientation, but not the stresses in the polycrystal. So now let's look at the functional dependence of crystallographic spin. So the general form I've written up here is that G dot, remember that's the rate of change of the 3 Eulerian angles, is a function of the orientation of the crystal, the imposed strain rate imposed on the aggregate, the texture that exists already, sort of the background texture, so to speak, the 3 critical resolve shear stresses, and the power law exponent. So it's a function with lots of arguments. So we use dimensional analysis to show that the spin depends only on the 2 independent ratios of the tau superscript s. So I used these 2 variables here, p12 and p13, which are natural logarithms of those ratios. Now another problem you will have seen immediately is that obviously I can't consider every possible texture and the influence of those textures on the slip rate. So what I'm going to do is restrict the texture space to a subspace of all textures produced by triaxial straining of an initially isotropic aggregate. So it's a well-defined subspace of the textures. And that subspace can be characterized by the 2 independent ratios of the axes of the finite strain ellipsoid. So here I'm using, again, a logarithmic form with R12 and R23 being defined as the logarithms of the ratios of the finite strain ellipsoid, the axes. So the simplified form that gives us is G dot equals a function of G, E as before, R12, R23, that's these ratios here, P12, P23, that's these ratios here, and the power law index. Okay, well let me just introduce the idea of slip system specific Eulerian angles. The idea here is that you put the normal to the slip system, or the normal vector to the slip plane, and the slip direction are both in this plane. In the plane it corresponds to psi dot. So when you slip on that slip system, you get vectors that look like this. You use your right-hand rule, and you find out that the spin is perpendicular to that plane, and it's the only spin, the only component of the spin that you've got when you define your n and l in this way. So as I say here, psi dot superscript s is the only non-zero component of the spin when you define your Eulerian angles correctly. Now, this next slide just shows you a bit the motivation, or how we came by these results. What I did was to use the SO model for uniaxial compression. That's a good case because it's symmetric around the compression axis, so you don't depend on the Eulerian angle phi. You only depend on the 2 Eulerian angles psi and theta. So you can plot your slip or your spin as on these 2-dimensional diagrams. So what you see is that at the initial instant, when the texture is isotropic, and you calculate the spin, the instantaneous spin at that time, you get a function that looks like this. Then you run the model a bit further to a strain that's higher, and you get a spin that looks like this. Well, they look like the same function. This is very surprising, and it turns out they are the same function. So the observation is that psi dot 1 is equal to this combination of trigonometric functions, very simple. And you can fit that, this unknown amplitude B can be fit to match the maps you see here. You get 1.25 at the initial instant, 1.71 down here at for a larger finite strain. And the variance reduction to the fit is 99.9%. So that's a hint already of what I mean by an exact agreement with the second order model. So preliminary implications of this, we have to test these things, of course, is that the orientation dependence of the spin is a generalized spherical harmonic of degree 2. This thing is such a generalized spherical harmonic. And the second implication, the very surprising one, that it's only the amplitude of the pattern which changes as the deformation progresses. It's not the pattern. The pattern is the same in this case and this case, but the amplitude is a function of the deformation. Okay, well now let's look at the spin due to a slip system which we'll label S. And this is an ansatz, something we're going to try and to see if it works. So we take the spin, the psi dot, and we write it as a product of 4 pieces, each of which describes a different aspect of the preferred orientation. So we first have a function, an amplitude function h, which controls the dependence on the slip system strengths. Remember, those were the variables P12 and P13. Then there's a second piece which gives the dependence on the existing texture, the texture we have right now as we're doing the calculation. Next comes dependence on the slip system orientation. You can see that by the definition of this so-called Schmidt tensor here. It contains the direction of slip and the normal to the slip plane for a slip system S. And finally, we have a dependence on the imposed deformation, which is just defined as an imposed strain rate tensor. Just to mention, this combination up here is suggested by a simple analytical solution for a polycrystal with only one slip system, so we're guided in a bit by that solution. So I'm going to try to show you now the different the expressions for these different aspects of the spin. So, first of all, the spin due to a slip system S, we're writing this now in an expanded form. It turns out what we do is we fit this ansatz to predictions of the SO model, to get the coefficients. And we find, in fact, that only 2 of those coefficients, the coefficients Qi, J, Kl here, in fact, only 2 of them are independent. And so I call those independent parameters B and C. And I'm getting all messed up here. There. So the pieces I'm going to show you now in more detail are these ones circled in color. Let's start with the red. That's remember the Schmidt tensor, which carries the information about the orientation dependence of the slip. So here's an example. The Schmidt tensor for slip system 2 of the 3. Not to worry about the details, it's just to show you that in fact they're all can be expressed in terms of generalized spherical harmonics of degree 2. You can see that by the things, the sine 2 theta, the cosine of 2 phi, and so forth. They can all be expressed in terms of generalized spherical harmonics. Here's the amplitude factor, H, which, as you recall, governs the dependence of the spin on the relative strengths of the slip systems through the variables P12 and P23. So it's a very simple relation that we find. We parameterize this in terms of a quadratic polynomial in P12 and P23. And using these transformation rules, which are just based on symmetry, you can get the same function for slip systems 2 and 3. So now finally, the amplitudes, remember the two independent components of the tensor Qijkl, the only two independent components, and each of those components depends on the ratios of the axes of the finite strain ellipse. So that's what you see here as the abscissa and ordinate. So the solid lines here are the best fits to the second order solution. And then these black lines, we smooth them using a function which is shown as the dashed lines. And those are simply fourth order polynomials. And they work extremely well for both the coefficient B and C. So this is a diagram due to one of my colleagues. I think it was James Wookey who did this. But it explains nicely the difference between the two methods. So the self-consistent model, the SO self-consistent model, works as shown up here. What you're doing is starting with a particular microstructure and evolving that forward to the next by a strain increment. But to do that, you have to enter into a loop here, which is highly nonlinear, where you have an iterative solution of these nonlinear equations here, because F has not been approximated by anything. And that typically takes, 100 or more iterations to get a good solution. By contrast, in the analytical parameterization, we have the analytical function for this thing, so there's no iterations that need to be done. The finite strain ellipsoid encodes information about the past deformation, and that enters into these quantities here. And so after we do the strain increment, we have a new finite strain ellipsoid, which we use for the next step. This is not to say that the texture depends on the finite strain ellipsoid alone, but it's a way of approximating or reducing the textural space we have to consider. So let me now show you some comparisons between the ANPAR model and the SO model, starting with uniaxial compression with these values of the R and P variables. So the compression axis is vertical here, and some of you may not know what these diagrams are. They're called pole figures. You take a hemisphere like this, and you've got lots of vectors which pierce that hemisphere at different places, depending on their orientation. And so the red points there would correspond to places where lots and lots of vectors pierce the focal sphere, so-called. But the main thing to note is the comparison between the two. So if you look at this, it's really a very good fit. The variance reduction, again, is 99.9%. And as you see, even the small details of the contours look the same in the two cases. You really can't distinguish them. But the real surprise, or the pleasant surprise you get out of this, is that it costs you 18,000 times less to get this new result as opposed to running the SO model through its iterations. So here's a case of pure shear now, with the compression being in this direction, extension being in this direction. And here you get 99.3% variance reduction, speed up factor of 31,000, And you see again, there's some very fine details that differ, but in general, the two sets of pole figures are essentially identical. Here for simple shear, now in this case, the shear plane is the red line. The sense of shear is shown here. The black line is the direction of maximum instantaneous extension, and the blue line is the long axis of the finite strain ellipsoid. But here again, 99.5 variance reduction, and a speed-up factor even more, 56,000. So a final case, comparison case, is for a slightly more realistic situation where you have a model, the classic model of a ridge crest, in which you have a wedge-shaped plate that's moving to the right here. It's pulling fluid up, and when the fluid arrives at this boundary, it magically becomes solid. It becomes part of the plate and is carried away. So here again are the pole figures for the SO model and for the ANPAR model. They're again essentially indistinguishable by looking at them. The variance reduction is 99%, and the speed-up factor is 58,000 in this particular case. Okay, well that's the main what I wanted to say about the ANPAR method. I wanted to describe now some work in progress in which we're representing textures using what I call structured basis functions. So the observation is that this equation, this evolution equation for the, oh boy, what happened? Oh, it gives me this.
Later.
I can't do that with a, I can't do that with a, good, okay, I don't know why it does that. So we have this evolution equation here, and it turns out that that equation has an analytical solution, somewhat complicated, but nevertheless analytical, if in the limiting case when only one slip system is active in the aggregate. However, there are a total of S such solutions, one for each slip system. And the advantage of these functions is that each solution automatically becomes more concentrated as the deformation proceeds. And that's why I call them a structured basis function, or an SBF, because they grow with the deformation. It's not like, for example, spherical harmonics, generalized spherical harmonics, in which you need more and more of them as your texture gets sharper. In this case, you can imagine representing arbitrarily sharp textures using just a handful of these structured basis functions, equal in number to the number of slip systems. So here's just an explicit form of one of these things. I'm using slip system specific Eulerian angles, and epsilon 1 dot, 2 dot, 3 dot are the principal strain rates. Here you see the equation, basically. This is an expression for the spin that comes out of the solution. And you can solve this equation by the method of characteristics, and you get a solution down here. As I say, a bit complicated, but it has the virtue of being an analytical solution which gets more and more peaked as the deformation proceeds. So here's an example. I'm using uniaxial compression again because the uniaxial compression does not depend on the Eulerian angle phi. So you've only got two angles. And here you see the three slip systems. Remember, there's a structured basis function for each slip system. So here are the three dominant slip systems of olivine. And this shows the basis functions as a function of finite strain. So here is a somewhat low finite strain. Second column is a larger finite strain. And what you can see is it's essentially the same function, very similar function, but the amplitude is getting larger here. It's getting more peaked. So now how do we put this all together? We've got 3 of these structured basis functions, and we want to express an arbitrary texture in terms of those. So we start by approximating the ODF, remember that's the orientation distribution function, as a weighted sum of these structured basis functions. So there's the approximate form of this solution is the initial isotropic orientation distribution times this bracketed quantity here, where the f sub s are the structured basis functions for each of the slip systems. C sub s is an unknown coefficient. So now we substitute this hypothesized expansion into the evolution equation, and we minimize the residual error. We try to get this thing to satisfy the evolution equation as well as we can, and we get this set of equations here. It's a coupled set of equations for the Cj, for the 3 expansion coefficients that you see up here. And the coefficients, alpha ij, beta ij, and gamma I, can be calculated in advance. So what you've got is an initial value problem for the coefficient Ci. So here, let's make let's look at an example again. So I'm comparing now the second order model with the structured basis function model. The example is olivine, of course, with 3 slip systems, just as I've been doing all along, deformed in uniaxial compression to a ratio of the axes 1.52, just an arbitrary value. Here are the results. You see, for the second order self-consistent model, you get a prediction that looks like this. It's very granular because you have the second order model works with a large ensemble of grains, say 2,000 grains. So you're trying to represent a continuous function in terms of grains, and you get this rather granular looking approach. The structured basis function approach has the advantage of working with continuous functions completely. So this is the prediction we get for exactly the same parameters here. So as you see, it's very similar to the SO model, but just much smoother, more pleasing to deal with. Another thing we get out of this, we pick up another factor of 100 in the speed. So down here, I made the explicit calculation for this here. And the structured basis function method is faster than the SO method by a factor of 2 times 10 to the 6th. So we've really got something that can possibly be used in the context of a very complicated convection simulation. So let me just some summary and perspectives from this. First of all, concerning the ANPAR, or the analytical parameterization approach, it has several advantages. One, it's in exact agreement, or 99.7% variance reduction, with the second order homogenization model of Ponte Castaneda. You have smooth analytical expressions for the crystallographic spin. You don't have to discretize in terms of grains. And the calculations are around 30 to 60,000 times faster than the SO method. So just some points about future work. We want to extend this approach, the ANPAR approach, to lower mantle phases. This is a project dear to the heart of James Wookey, who's encouraging that we do that. Extension to 2-phase aggregates would be another extension. For example, olivine plus enstatite for the upper mantle. We also need to parameterize recrystallization in some way. This is a little trickier because we don't really understand well the mechanisms of dynamic recrystallization. But that's important because laboratory experiments show that recrystallization can change the orientation of the crystals. Fourthly, we want to develop this structured basis function approach. All I've showed you so far was one simple example for uniaxial compression, but we want to develop this so it's applicable to an arbitrary deformation path in the mantle. And finally, we hope to make a user-friendly open source implementation for this at some point down the road. So I see I have lots of time left, but I'm done. So that's all. Thank you.
So plenty of time for questions. Okay.
Neil, if your colleague hopes to pursue it, and you hope to pursue this for materials like perovskite, what do you use for you have good single crystal data because it came from my lab for olivine, but you don't have anything for perovskites.
Yeah. Well, if you've got no information, we can't get very far. I mean, one thing you can do is you must have some hypotheses on what the dominant slip systems are.
Yeah.
So you can.
Nothing quantitative.
I see.
I guess you could say these are the slip systems, but I think you'd be hard pressed to come up with robust data to.
I see. Well, in that case, then the method has to be used with a grain of salt, with lots of salt. Because it's.
So I guess you can kind of hypothesize.
Yeah, you could assume some number of slip systems and do the model for that, but then you're just realizing that your results are no better than the initial assumptions.
I think the SO model breaks down at high strains. I don't see any reason why this should break down at high strains, but does it give you, I mean, you can't then compare the two because one of them is broken down, but does ANPAR give you the expected result that if you keep evolving, eventually this fabric stops changing?
It moves towards a single crystal fabric in a sense. Yeah, that's a problem with all of these models, that there's no limiting factor in them. So in fact, one of the things we're trying to do, one thing I think we can do with the structured basis function approach, is put in a kind of limiter, some kind of function that would limit the strength or the peakedness of the texture. But I agree with you, it's a serious problem that these models don't address.
Along a similar line, I mean, for your evolution of a model for the structured fabric, you've only got an advective term. Does that, if you compare with experiments, are there other physical effects that are being left out of them?
I'm sorry, other physical effects?
I mean, is there ever any sort of diffusive character of term for the fabric?
Oh, well, I mentioned at the beginning, this is only valid when the rocks are being deformed in the dislocation creep regime. I mean, generally, diffusion creep, what's that? Diffusion creep doesn't produce texture. So this is assuming necessarily that you're in the dislocation regime, which I think is not a bad approximation for the upper mantle because we see anisotropy all over the place. So that seems to argue that you should have dislocation creep.
But you mentioned recrystallization. Does that potentially be an additional term in the CO?
Yeah, I think so. I think it might be recrystallization that prevents the texture from saturating at some very very strong value.
Yasuko's colleague Takehiraga has done some nice experiments in the diffusion creep field and shown that because the grains can have a shape-deferred orientation just due to their crystal anisotropy. And it's basically the idea that you rotate the grains due to their shape rather than dislocation.
Oh, I see.
Is that kind of thing possible to build into your code?
That's a very nice comment. I'd like to say yes. I don't have a clear picture of the path yet, how to get there.
And that would, from our perspective, doing experiments. It would really be extremely powerful if that were.
But now, tell me if I'm wrong. If the grains get too elongated, don't they tend to break up by recrystallization, subgrain
These
rotation?
grains since there's no dislocation activity, at least his argument is if there's no dislocation activity, then the grains basically are controlled by the crystallographic and the surface energies of the interfacial energy in the system.
Uh-huh. Can they attain a large aspect ratio, or do they break up?
They're relatively small aspect ratio, but maybe 1 to 1.5. You know.
Oh, okay.
A ratio of 1.5.
Okay. Yeah, there's some of the self-consistent models do have a grain shape option. I'm confess I'm not sure how much of an effect that is.
I have a very naive question, which is that I've never understood how you define spin in these problems.
Mm-hmm.
What's your reference frame?
Well, the reference I'm thinking of the reference frame as being in the well, what we're doing in this approach is taking the finite strain ellipsoid as a reference frame and allowing the imposed strain rate from outside to be non-diagonal. Does that answer your question? I think
Really?
I think the finite strain ellipsoid is a good reference frame.
But I mean then clearly I mean, you can't define spin in terms of the reference frame of the deformation, right? If you define it in terms of the finite strain ellipsoid. I've never understood how you define spin in these problems. People, I mean, you know, the way in which you calculate it to get the finite strain ellipsoid, you use a quite arbitrary set of axes which you yourself define.
Yes. Uh-huh.
Right? But the deformation can't know anything about those axes.
Yeah,
But the
that's a good point.
deformation must be invariant with respect to rotations.
Oh, invariant, you say?
Invariant.
Uh-huh. Uh-huh.
Yeah, it can't know anything about them.
Well, the calculations we've been doing here, the ones that what I showed, the comparisons, are basically done in a lab frame. The frame of the device that's.
Well, I mean, that's fine, but you know, that can't be a general result.
Okay, I haven't thought of it in quite that way.
I have a lab frame.
No, no, I haven't. That's a good point. I haven't thought of it in quite that way, but I'll have to reflect
I
on
never
that.
understood that.
I'll have to think about that.
issue.
So I'm a little unclear on your comment. I mean, isn't it the crystallography that defines the orientation of the spin? Because it's defined by.
So
being
you
normal
fix
to-
it, but if you fix it to the grains, right, then by definition the grains are not spinning.
Yes, right.
That I don't think quite works.
I mean, one way to do it is to use the principal axes of the strain rate tensor, of the global strain rate tensor.
I think that. No, you
Would
can't,
that work?
you
Would
can't
that
use
work?
no, you can't. You clearly can't do it with the global strain rate. You have to do it as a local strain rate tensor.
Well, the local strain rate tensor varies among grains.
Well, it depends between my global. I mean, if you're in corner flow,
Yes.
right, there is no global strain.
No global strain. I'm sorry.
It doesn't define. It doesn't define a set of axes.
No.
Okay, so then you, I mean, if you want to use the instantaneous strain rates, right, then you have to define it at every point within that corner flow.
Okay.
And then you get rather strange things that are going to whiz round. All kinds of things are going to happen
Okay.
if you do that.
Well, let's talk about this afterwards. I confess I haven't thought about it in quite this way.
I mean, I'm not sure I have anything more to say other than that I've never understood it.
Okay.
Other questions or comments?
Is there time for more? What if have you tried applying a kind of compound? All of the experiments you've shown us are for a single orientation of the strain. If you had a compound orientation, you shear it in one direction and then you develop a fabric, then you stop and you shear it in another direction. Does everything work equally well?
I'm sorry, if you do a sweep in one direction and then,
You've started with a random
yes,
initial condition, and you imposed a constant, I think, strain rate on it, not a constant stress. But
yes, it's right.
and then you develop a fabric, and then you plot the fabric, and you're done. But what if you either say, I'm going to start with a non-random fabric, or
Oh,
you run
yes,
the model
I
once,
see.
stop, look at the fabric, then run it with a different orientation of strain? Does
Yeah,
it
in,
break?
prin- in
Does it work?
principle, I haven't tried it,
Yeah.
but in principle it should work. Yeah, because you've got all you need is an estimate of the finite strain ellipsoid to get the spin.
Yes, I have a related question. At some point you mentioned that knowing the finite strain ellipsoid encodes some information about the previous deformation.
Yeah.
So on a similar line, let's say you take some material that's already been deformed a lot, and you don't know how it's been deformed, but you know its texture. You want to use that as an input. You want to use that as a starting place.
Yes.
How do you get an estimate of the finite strain ellipsoid if you don't know what it was?
Yes, that would be tough. I don't know quite how I would do that. This is essentially, this assumes a progressive deformation path where you know everything along that path.
Starting from an initially undeformed state.
Yeah, or you could start from a state whose origin you know. If you know the path it followed, its deformation history, then you could continue it.
What else? Yeah, I'll do.
Just if you know the texture, you don't know to need the previous deformation history. You only need to know the forward. You need to know the previous deformation history if you don't know the texture, and you have to model the texture evolution until this point.
If the finite strain ellipsoid is something that's
You just
underlying
know-
this.
You just need for propagating it forward. If you know the texture.
Okay. You would start with some initial distribution, but you would take the finite strain ellipsoid to be spherical.
No, you need to know which will be the finite strain ellipsoid that you accumulate in the step where you're making your texture evolve. So the forward one.
All right, anyone else? So we're ahead of schedule. Why don't we break for 10 minutes for a cup of coffee if you want, and we'll come back in 2:30. All right, and let's thank Neil again.